Hello everyone, and welcome back to the Kohi Game Engine series. Today we are going to tackle creating a texture system. I would like to take a quick second and thank the supporters of the channel, beginning with our partners, Eearslya, Wensheng, and Caden. They are the partners of the channel, which is the highest tier of support for the channel, so thank you very much for that. And I would also like to thank all the other supporters listed here on the screen. Your support is very much appreciated, so thank you for that. Okay, so over the course of the last several videos, we've done some work with images and textures and getting our shader to accept those textures. And today we're actually going to enhance things a little bit further because we've got a lot of temporary code and sort of temporary hacks that we've put into place to make a lot of this stuff work. And so, at least in terms of textures, we're going to start to fix some of these temporary hacks and batten down the hatches and start coming up with a system that's a little bit easier to use and more flexible, and more importantly, more decoupled from the rest of the system, right? And so to do that, we are going to create a new system, a texture system, that is responsible for generating and loading textures, right? And it will interface with our renderer to upload any texture data to the GPU as needed. But it'll give us a sort of global way to access textures. However, before we jump into that, there is some additional preparations I want to make and some changes that I want to make, because I've mentioned a few times now that I haven't really been too fond of the Vulkan object shader name itself and the name of a couple of other things within the system. And so I want to make some changes to some of this to make a little bit more sense in the direction that we're heading, okay? And so in this video, we are going to crank up the old refactor tractor and take the old girl around the block for a walk, okay? And the first thing that we're going to do is we're going to start with this object shader. Now, this object shader deals with individual objects within a scene, right? But realistically, if we look at some of the properties that it already has, we have a diffuse color and a diffuse texture, and we're going to have some other properties available as well. And what do these things really describe? Well, these things really describe the surface of an object, right? And when we think about the surface of an object, it has lots of different properties. It has some surfaces can be shiny, some surfaces can be rough, some surfaces are smooth while others are bumpy, and all of those things have different properties, right? And that's because all of these things in the real world are made out of different materials. You have things like wood materials, or you have tile materials, metallic materials, things of that nature. And so I'd like to actually start thinking of some of these things as materials, right? And this is eventually going to be sort of a stepping stone to a material system, right? So before we can actually create a material system, we actually need to talk about what a material system would need to know. And one of the first things that a material needs to know is what the surface looks like. And of course, that relies on a texture system. So before we can actually create our material system, we need to create our texture system. However, before we do that and jump into that, I would like to rename this Vulkan object shader to Vulkan material shader, because this ultimately is going to be a representation of materials in the world. And we are going to basically be building this to accept different properties of materials for different surfaces in the world, whether it be various static objects or maybe an animated character or even terrain. All of these things are different types of materials, right? And so it makes sense to begin referring to this as a material shader, because ultimately that is the type of thing that we're dealing with, right? So this Vulkan object shader doesn't really make sense. Vulkan material shader, I feel, makes a lot more sense. So the first thing I'm going to do is I'm going to go to our definition of Vulkan object shader, And I'm going to hit F2 to rename, and I'm going to rename this to Vulkan Material Shader. And that should rename it across all files, so I'm just going to go ahead and hit Save All. And we see here that it's gone ahead and changed those things in these couple of files, right? And I believe there's actually some other places we're going to have to change this too, but for now this is fine. Okay, so the other thing that I'm going to do is I'm going to go ahead and rename all of these to reflect the Vulkan Material Shader name. So I'm going to do this off camera just for expediency. Okay, so we've got those all renamed, so I'm just going to go ahead and save all again. And so the next thing that we need to do is we need to rename anything that is referencing these types, right? And predominantly that is going to be in the Vulkan backend. So if we take a look at our Vulkan context, we have our Vulkan Material Shader here, but the name of this actual variable is still Object Shader. So I'm going to rename this as well to Material Shader. Okay, and I'm going to go ahead and save all again, okay, because that affects a number of files. Next, I'm going to go ahead and rename the files themselves. Okay, and of course this means that anything that is including Vulkan Object Shader.h is going to be wrong, so I'm just going to do a find and replace on the whole solution for that. Okay, and I'm actually going to get rid of this quotation there, so that way anything that is including this h file goes ahead and gets updated to use the new one. So we'll go ahead and do that. Again, just make sure that everything is saved. All right, and then one more thing we're going to do is we're going to go to Assets, under Shaders, and we are going to rename our built-in object shader to built-in material shader .frag GLSL, and we'll do the same for the vertex shader. Okay. Since we've done this, that means that we also need to come down to our post-build batch file, and we need to replace object shader with material shader. So we'll replace all those, and we'll do the same thing in the sh file, the bash file. Okay, so that way our files are renamed here. Now obviously, since we've done this, we'll also need to come into the Vulkan Material Shader, and we have this built-in shader name object, which is called built-in.objectShader. So this is what actually finds that. So I'm just going to go to the definition of that, and we are actually going to rename it first off to material. Okay, and it doesn't look like for some reason it actually did this. So I'll go ahead and do that. And then I'll also replace the object shader with material shader here. Okay. And that should be all that we need to do to make sure that this is hooked up. So one thing I'm going to do real quick is I'm just going to go ahead and build this just to make sure that everything runs as we expect. And it looks like we missed a file. So no rule to make targets. Okay, so if you guys actually get this, that is because we have an object file for something that no longer exists. So I'm just going to clean and rebuild. Okay, and it looks like we have another error. So we have an implicit declaration of, okay, so it looks like one of our renames didn't work. So we have an implicit rename here. So this should be material shader, acquire resources. Okay, and let's go ahead and build that one more time. Okay, linking. Looks like we are good to go. Okay, So that should be fine. One more thing I'm going to do is I'm going to run task and then post build just to rebuild our shaders, and it looks like it actually emitted the correct shader file. So I'm going to go ahead and run the application, just make sure that everything works as we expect. And we can see here that everything seems to work just as before. So great. Okay, so now that we're done with that, there are a couple of things that we need to add that are going to support the work that we need to do. So the first one of those things is we actually need to add something to our string library. And this is going to be a rather simple function. So right here we have strings equal, which is a case-sensitive string comparison, where you compare these two strings and we return true if they're the same, otherwise we return false. We're going to need a case-insensitive version of that, right? Because of the way that our texture system is going to work, right? So I'll explain more about this when we get to it, but we need to go ahead and add this now so that we don't have to break and add it later. So since we have added that function, we need to come into the C file. And right below strings equal, we're going to paste our definition of strings equal I. Now, these are not standard functions that are available. These are sort of extensions depending on the type of compiler backend that Clang is using. So on Windows, we're actually going to wind up using this underscore string comp I, which is a case insensitive method that comes with Windows. And then otherwise, for Linux and Mac and those other platforms, I believe they all actually use this. In our case, we're actually just going to say if we're using GNU-C, we're going to use string case comp, right? And this is the case insensitive comparison, okay? And so in order to actually use this on the other platforms, we're actually going to need to add a small include to the top. So if we are not using Visual Studio as our backend, then we are going to include a file called strings.h. That is what includes this function right here, okay? So that should make it work on all platforms, okay? All right, so that is it for the string library for right now. The next thing that we need to add is something called a hash table. Before I jump into hash tables, one of the things that our texture system is going to give us the ability to do is to reference textures by name. So whenever we load a texture, we are going to provide the name of that texture, and that's going to be used as part of the file path to load the texture, and eventually we'll be enhancing that as well. But anytime we need to get a reference to that texture, we're also going to do that by name. And then anytime we release it, we are going to do that by name as well. And so we need a quick way to look up something by a string, right? And we don't want to be doing a string comparison because that's not the best way to do it, right? It's not exactly quick to look up that way, right? So say, for example, you had an array of texture entries and each one of those had a name, and then you had to do a string comparison on the name of each one of those entries. That's not fast, right? And so there's a data structure called a hash table, and we are going to be implementing a very simple one of those today, where a hash table basically takes a string, and we're going to call it name, and it runs that string through a hashing algorithm and returns an integer that is unique. And that integer is then modded against the total size of the hash table, so that'll be the total number of entries that the hash table can hold. And that final number winds up becoming the index into an array. So what you do is you feed in a string, it gets run through the hashing algorithm, that returns us a number. That number is then used as a quick index into an array to obtain the data that is at that index of the array, okay? So that is more or less what we're going to be doing. There are some fancy hash tables that are capable of resizing on demand. We are not going to be implementing one of those. What we're going to do is we're going to implement a fixed size hash table where you declare up front how big you want the hash table to be, sort of a maximum number of elements. And then from there, you can go ahead and add elements to it, okay? And once it's full, right? And that sounds kind of limiting, but most of the time, it's actually not a huge limitation, right? The only thing to be aware of is one potential pitfall with hash tables is that you can have what's called a collision. And that is where the hashing algorithm can generate the same number for two completely different strings. So one of the best ways to avoid that, obviously, is to have a large hash table with a very large amount of entries, right? Because the more entries you have, the more unique numbers you can have. And another way you can get around that is by basically creating an array at each index of the array. So you'd wind up with a two-dimensional array, and you just simply push a additional entry into that array at that index, right? So you can have an array of linked lists, or you can have an array of arrays. There's a bunch of different ways to do it, but we don't want to use any of those because we want to avoid dynamic allocation wherever possible. So the idea here is that we want this to be as fast as possible and hopefully avoid collisions as much as possible. So in the case that we collide here, we are not going to be pushing an additional entry. All we're going to do is we are just going to overwrite the entry, right? And all this means is that if you find that you have a collision here and one texture sort of gets replaced by another, then just name it something else and chances are you'll probably be fine, right? We could do something more robust. We may expand on this later, but for now I want to keep it simple because I need this to be sort of in here quick so that we can move on to the next step, okay? With all that said, let's go ahead and add our hash table. So this is a container, so we're going to add it under containers. We're going to create a new file called hashtable.h. Of course, we'll start off with a pragma once and an include of our defines. And we're going to start off with a simple structure here. So this is our hash table that will actually hold everything that we need. And it's got a number of properties, right? So here is the size in bytes of each individual element in the hash table. So this hash table will only deal with one type of element at a time. So we won't have variable sizes between elements. This allows us to keep things very lean and mean and fast without having to worry about different sizes or maintaining a free list or anything like that. Here is our element count, so that's going to be our maximum element count. We have a Boolean to indicate whether or not the type of data that we're storing in the hash table is a pointer type, because we actually have to handle things slightly different for those cases. So if we have a hash table that whose values are all integers, that is handled differently than if we have a hash table whose values are all pointers to integers, right? Or structures or what have you. So we actually need to know that during creation. That way when we call the methods against it, we know what is valid and what isn't. We also have a void pointer here, which is a memory block to hold all of the elements in the hash table. We also have a debug count value here, and I'm not going to implement this initially, but what we might wind up using this for is every time we call set, we might just increment this, and every time, you know what, in fact, I'm not actually going to use that. Let's just keep this simple, right? So these are all four things that our hash table is going to hold. I did make a couple of notes in here. So for non-pointer types, the table returns a copy of the value. And for pointer types, there are certain getters and setters that we are going to have to use that are separate. I'll get to that in a second. Should also note that the table does not take ownership of the pointers or associated memory allocations with those pointers. Those must be managed externally. So whatever is actually creating the pointer to be added to the hash table should be the one that manages it, not the hash table. When the hash table is destroyed, those pointers will not be freed. So just bear that in mind. Okay. All right. So our API for this is going to be pretty simple. The first thing we have is a hash table create. So this basically just creates the hash table and stores it in our out hash table. So this is going to take a element size, the element count, a already allocated block of memory, whether or not it is a pointer type, and then of course it's going to output our table. Pretty straightforward stuff. Obviously, since we have a create, we need a destroy. So there is our destroy. It just takes a pointer to the table. Next, we have a set. So this stores a copy of the data that is provided in value in the hash table, right? So here's the hash table we're going to store it in. Here is the string name that we're going to store it under, and then a void pointer to the value. So typically this would wind up being an integer or something, and we would dereference this and take a copy of that value. Or more accurately, we're going to use memcopy essentially to take a copy of that, okay? So that is the copy version of that. And then, as I mentioned up here, we have a pointer version of this as well. So for pointer type tables, this stores a pointer as provided in the value to the hash table. And note that this is a double pointer, right? So it's a pointer to a void pointer, okay? And the reason for this is it basically, since it's a pointer type, we want to store the memory address of the pointer, not the actual value that's in it, okay? So this is called hash table set pointer. So anytime we create a hash table with is pointer type set to true, this is the method we should use. Otherwise, we should use this one, okay? Next, we have our getter. So this is the copy version of that. All this does is take a pointer to the out value to store the value, and of course our table and what name to look up, okay? Obviously, we have also a pointer version of that. So this just does the exact same thing. It just returns or sets a pointer. And then one last thing that we have in here is something called fill. And this fills in all available entries within our internal hash table, right, within our memory block here, with the value that's provided. Now, generally this isn't something you'd want to do, but if you want the hash table to sort of have a default value for anything that you look up, then you would need to use this. And in fact, we are going to wind up using this for our texture system, right? So in our case, we're going to have texture lookups that we want to have a default value and not just a value of 0. So we are going to wind up using this, okay? So it just fills the entire hash table with whatever is provided in value. And that is it. That's our API. It's actually pretty straightforward. So under containers, we're going to create a new file. We'll call that hashtable.c. And this I'm really going to blaze through because I don't want to spend a whole lot of time on this. So actually, let me get rid of this console and this one. Okay. So first, obviously, we are going to include hash table. We also need k-memory, and we're going to need our logger. Okay. And the first thing that we're going to implement is our hashing algorithm. And this is it right here. It is super dirt simple, right? So we have a function here called hash name. It takes in a string. It takes in the total number of elements within the hash table. So this is something that we'll be calling from our methods to actually hash a string. And then we use a prime number multiplier to help avoid collisions. And I'm not going to go into all the reasons as to why that is, but generally speaking, when you're generating a hash against a string, you want to at some point multiply it against a prime number, and that helps avoid collisions, okay? So basically what we're going to wind up doing is we are going to convert, or we are going to treat the name as unsigned characters, right? And we're going to do that so that we can actually add them together. And then we're going to store a running sort of total for the hash, right? And so what we're going to do is we're going to loop through each character of the string, and we're going to do that by casting name to an unsigned const character, right, which is going to give us a U8. And then we're going to set US equal to obviously the first one, right? So this is going to start at the first, And then the for is basically going to just dereference the US and say, well, this exists. So in other words, as long as this isn't 0 or the null terminator, then it's going to move the US pointer forward 1, and that essentially just moves the character forward 1, okay? And then we're going to say hash is equal to hash times our multiplier up here times the dereferenced value of US, okay? And it's going to continue a running tally of that until we get to the end of the loop, or the end of the string. And then it's going to take that amount and mod it against the element count that we pass in. So in other words, it's going to mod it against the size of the table, and then finally return it. So this is not a fancy hash algorithm. There are other ones out there that are known to prevent collisions better than this. But if we run into problems with it, we can always swap this out, because all hashing algorithms basically take these parameters and return a number. Okay, so this is the one we're going to use for now because it's nice and simple. If we need to switch it out, we'll go ahead and switch it out, but for right now, we're not going to do that. So next, I'm going to basically step through all of these functions here in order. And again, I'm going to go pretty quickly about this, right? Because most of it should make sense to you guys just by sort of looking at it. So the first thing that we do is we confirm that we have our memory. So confirm that that exists, confirm that out hash table exists. If it doesn't, we bleat about it and return. We do the same thing for element count and size. Neither one of those can be 0. So if either one of those is 0, we bleat about it and return. And then here we go ahead and just set the memory. I have a to-do in here to where we might want to require an allocator and allocate this instead. But for right now, this requires the memory to be allocated outside of the hash table and just passed in. So we copy over the memory, the element count, element size, whether or not it is a pointer type, and then we go ahead and 0 all of the memory block, right? So that is pretty much all there is to that. Destroy is pretty straightforward too. All we're doing in this case is just zeroing the memory, if of course the table exists. Okay, so the copy version of the set basically just makes sure that there's a table, a name, and a value. If any of those are non-existent, it bleats about it and boots out, returning false, meaning failed. And then if our table is a pointer type and we've called this, we actually want to bleat about that too, because we don't want to use the non-pointer methods with a pointer table, and vice versa, right? So we're going to actually check this whenever we go ahead and set, okay? And this will actually give you an error saying what you did wrong and return. Next, we go ahead and generate our hash just by calling hash name and passing the name and the table's element count. And then we copy memory by taking the memory, the address of the table memory, and adding to that the element size times the hash. Now remember, the hash is the index into the array, so if we take the element size and multiply that by the hash, we'll get the memory offset and bytes from the memory, right? So if we take that, that'll actually give us our void pointer to copy into, right? So that's the destination. The value is the source. So we just take the value, we take the data that is in value, and then we take the element size of that, okay? And then we return true. All right, so that is the copy version of that. The pointer version of that performs some of the same checks, so it makes sure that the table and name exist. However, if 0 is passed to the value, it actually treats that a little bit differently. It actually sort of unsets the entry, right? So we do allow this to actually be passed as 0. And then, of course, we say if the table is not a pointer type. In other words, we're calling a pointer function against a non-pointer type table. We will bleat about that and return false. And of course, we take the hash of the name. And then here, we basically take the table memory, and that is a void pointer. We cast it to a double pointer, or an array of void pointers, right? And then we take the hash index to that. And we set it either to value. If value exists, we will take the value, the dereferenced value within value. Otherwise, we'll set it to null. So in other words, if 0 is passed here, we'll just set its value to 0, right? And that just gives us a way to sort of zero that out. Okay, otherwise it'll take the dereferenced data in value. Okay, and then we return true. So the get looks very similar. So here's the copy version of that. Again, we need table name and out value. We do a pointer type check. Again, we take the hash, and this time we copy the memory to the out value, right? So our pointer here, and we do the same method to get the memory offset, and we just copy that memory over, right, and return true. And then here is our pointer version of get. So all this does is the same checks as before. We take the hash, and then we dereference out value and set its value to the hash index of memory treated as a void pointer array. Okay? And once we do that, we also modify our return value a little bit here. So in this case, this returns a Boolean. So in all the other functions, we always return true. In this case, if we get a pointer here and our dereferenced out value is 0, then we're going to return false. Otherwise, we're going to return true. And that just gives us sort of a quick way to check to say, hey, was there actually a value that was returned from this, yes or no? So this function's a little bit different than the others, but there's a little bit more utility there. Finally, we have hash table fill. So again, we take our checks here, and once those pass, then we go ahead and say we want to take this value, and we want to loop through every element and copy the memory into that, okay? And of course, we return true. And that, ladies and gentlemen, is our hash table. It's nice and simple. I'm sure that we probably will wind up expanding on this or maybe making an adjustable version of it later. But for now, this is nice and simple, and that's the way we want to keep it. Now, the other thing that I want to do and start doing a little bit more often is I want to spend a couple of minutes creating some tests for this so that we can validate that our hash table actually does what it's supposed to do. Okay, so what I'm going to do is go under tests and under source, and I'm going to create a new folder, and I'm going to call this containers. All right, and under containers, I'm going to create a new file, call it hashtabletest.h, and all that's going to have is a pragma once and then a hash table register tests. Okay. Next, I'm going to create another new file called hashtabletest.c, and it is going to include a number of files. Obviously, our hashtabletests.h, our test manager, our expect, and then of course defines and our containers hash table that we're going to be testing against. Next, I'll go ahead and stub out our hash table register tests. And I'm basically going to go through and create a couple of quick tests, right? So the first one is should create and destroy. Basically, this just creates a hash table with 3 elements, creates it, validates the memory, the element size, the element count are all correct, and then destroys it, and then revalidates that those things all got zeroed out, and returns true if that's the case, okay? Pretty straightforward stuff. So the next thing is should get and set successfully. This is for the non-pointer version, right? So again, it creates a hash table, validates the size of those things. Then we go ahead and in this case, we're creating a hash table of U64s. So we create a test value, and we're going to set that to 23. And we'll go ahead and call hash table set, pass test1 as the name, and then the address of test val 1. So that'll pass along that 23. And then we have here our U64 get test val 1, which is sort of the reserved for the getter, right? We initialize that to 0. Then we call hash table get. We are going to get test1, that's the name. And we're going to pass the address of get test val 1. And then we just need to test that they're equal, right? So this should come back to 23, okay? And then we go ahead and destroy it and validate that. So that's all there is to that one. Next, we're going to test pointer types, but before we do that, we need to actually have a struct to test with. So I've created a simple struct here that has a Boolean, a float value, and a U64 value. And this is going to test get and set the pointer version successfully, okay? And this is almost the exact same thing as what's up here. The only difference is instead of U64s, we are going to be working with htTestStruct pointers, right? So that is our type for the table. So our element size should be the size of a pointer. We should have a size of 3 of those. And then we go ahead and create an htTestStruct, create a pointer to that by grabbing the address of t, right? Set those values, call our set pointer, right? And in this case, we need to cast that to a double void pointer and then take the address of testval1, right? So that passes it through as need be. So we're basically taking the address of the pointer and passing that through. And then we're going to do, similar to before, we're going to create a pointer, in this case a null pointer, to hold our new value. And what this should do is basically reach into the table and set this pointer equal to this pointer, okay? And then it compares the value of those things and then destroys it and cleans up, okay? Next, we do a quick test for non-existent entries. So just to see what actually comes through for non-existent entries. So in this case, we set one that is called test1, and we try to get a test2. And we should expect a 0 value in here since that memory is zeroed, should be at a different index, okay? And I've tested this to be true. Next, we'll do the exact same thing, but for pointers. So we have this hash table should set and get pointer non-existent, and it basically repeats the same process for pointers. Next, we're testing the unset logic of pointers. So all this does is goes ahead and sets a pointer as in the previous test, and then once we set that, we go ahead and verify that it returned as that it exists and is correct, right? And then we go ahead and we quote-unquote unset it, where we pass test1 again, and this time we pass 0. So this is that 0 functionality that I was talking about. So it should do that successfully, and then we should basically see that it is no longer found. So this should actually return false at that point, since that value is going to be 0. And then this should also be 0, right? Because it should be a null pointer. So this just tests that. Next, we try to call a non-pointer function on a pointer table. So this is just testing the interoperability on that. We make sure to output a debug message saying that the following 2 error messages are intentional, because this call and this call will generate error messages because we're calling the wrong version of this. This is a pointer table, but we're calling the non-pointer versions of these things. So we're just testing that that works and returns a false result as expected. And then we do the opposite and take a non-pointer table and call the pointer functions. These should also return false. And then finally, we do one more test against the pointer table, and we set a pointer, and then we get that pointer, and then we update the pointer value itself, right? So once we get this, we go ahead and change the values, and then without calling set again, right? Since this is a pointer, it should be the same thing. We go ahead and call get again, this time to a different variable, and compare between the two, and they should all be the same, right? So we should be able to update this, and the memory that that maps to should also update in the table because it's a pointer, so they should all be pointing to the same thing. So this just validates that that works the way that we expect. And then last but not least, we go ahead and hook up all these tests. Now, I realize that I've breezed over these, and there's a lot going on here, so I'm not going to go into these in any more detail than that. If you guys are interested in more details, I encourage you to open this file and have a look at the tests, okay? So finally, we just need to go ahead and go into main.c here under our tests, and we need to include our containers hashtable tests.h and also register the tests, okay? So I'm going to go ahead and build this and just make sure that it runs as we expect. So I'm going to go to the debug here and change from Windows Launch to Windows Launch Unit Tests, and I'm going to run. Okay, and we see here that 14 passed, 0 failed, 0 skipped. Now we do see some errors in here, but this is why we put the debug saying these the following 2 error messages are intentional, because these are sort of the negative tests that we're doing, where we're calling pointer functions against non-pointer functions, pointer functions against non-pointer tables, and vice versa, right? So those are those 2 tests generating those errors. So that's why we put this debug in here to let the runner of these tests know, hey, this is fine, okay? What's important is this, all these tests passed, okay? So that is it. I'm going to switch this back to Windows Launch, and we are going to forget about the hash table for now because it works. Okay, so now we can actually jump into our texture system. And our texture system is thankfully not going to be too overly complicated, right? It's actually, we're going to try and keep this as lightweight and straightforward as possible. So the first thing that we need to do for that is under source, we need to create a new folder called systems, okay? And this is where we're going to start putting our systems, and we're probably going to relocate some of our existing systems here and rename some things later. But all of our systems that we're going to create for our various pieces of data throughout the engine are going to exist here. So our first one is going to be texture system.h. And texture system, actually let me get rid of this. That. So our texture system obviously is going to pragma once, and it's going to use our renderer types, so we want to include that. And for this particular system, we're going to have a configuration. And the only item in our configuration right now is a U32 max texture count. And that's going to wind up being the maximum number of textures that this can hold, right? So this is going to be configurable. We can easily change this later on. Eventually, we'll actually hook this up to a configuration file too, so we can tweak and fine tune later on. Next, we want to actually define something for our default texture name. So a couple places in code, we are using this default hard-coded string. This, we're going to go ahead and define a macro for that so that we can always be sure that we're using the right thing here, okay? Similar to other systems that we've seen, we have an initialize and shutdown. So our initialize takes a pointer to the memory requirement, a block of memory, and then a config, right? And this takes this by value, not by reference, okay? So obviously this works the same way. You always have to pass a pointer to a U64 for the memory requirement. If state is passed as 0, then it calculates this memory requirement and boots out, at which point you would allocate the memory for this and then call it again, okay? This returns a Boolean for success or failure. And then shutdown, of course, just takes the state, okay? So the next thing in our interface is going to be our acquire and release methods. And this is where that auto release that we've talked about a couple of times comes into play. So whenever we acquire a texture in the system, we pass a name to say, hey, this is the texture we want to acquire. If that texture exists and has been loaded, it returns a pointer to it. If that texture does not exist, it attempts to load that texture and returns a pointer to whatever it is able to load. So if it's not able to load a texture, that'll actually point to the default texture until something loads. or if it's unable to load a texture, there may be some circumstances where this actually returns a null pointer. So we'll kind of touch on this on how all that works, right? But the important bit here is auto release, true or false. So the way that this is going to work is there's going to be a reference counter. So every time we call acquire for a texture, we're going to increase that reference counter by 1. If that reference counter reaches 0, meaning we release a texture by that name, and every time we release a texture, it decrements that reference counter. So if we release and that counter reaches 0 and auto release was set to true for that texture, then we go ahead and release it and unload it from the system, and then it no longer exists in here, okay? And that's done obviously to free up some memory, for example, when we unload a scene or something like that. And then for right now, we also have a utility method to get the default texture. So it just returns a pointer to the default texture that we previously had created in the renderer front end, right? So we're gonna wind up moving that logic to support that. So we're gonna have a few of these get defaults, but for right now, this is just the get default texture in general, right? The in general default texture. Okay. So next, we'll go ahead and create another new file under systems called texturesystem.c. And texturesystem.c is going to include a number of things. So it needs obviously the H file for that. We need our logger, we need our string library, we need our memory library. We need our new hash table because that is how we're going to look up our names. So you guys can see how that ties in. And then we also need a reference to the renderer front end. So we're going to need that as well. Great. So before we move on too much further, there is one thing that I want to change in our interface. So we need to go to renderer types INL and change a couple things. So the first thing that we want to get rid of is we don't need this default diffuse, right? We're going to actually manage that a little bit differently. So I'm going to get rid of that. And then the other thing is in this create texture, this auto release, we're actually not going to handle that at the renderer level. We're going to handle that at the texture system level. So I'm going to get rid of that there, which obviously means that anything that this points to needs to have all that stuff removed as well. So since we've done that, we need to go to our renderer front end and remove auto release from here, which means our renderer front end create texture. Whoops. Okay, so we need to remove auto release from renderer create texture, and then obviously from the back end as well, because we don't need to pass that through anymore. All right. And I know there's other errors in here. We're actually going to have to come back and fix quite a lot here, but we'll come back to that. So next, in the Vulkan backend, we also have auto release here. So I'm going to remove that. And down here, I'll remove that as well. And if you recall, that wasn't actually pointing to anything, so it's not a huge deal. So the next thing that I want to change is this Vulkan material shader create. So this actually takes a default diffuse, which we no longer want to use as well. So we're going to remove that because now we can use our texture system to get that for us. So I'm actually just going to set this to 0 for right now. And actually, you know what, while we're at it, we actually don't need to store this here. So I'm going to remove that from there as well. That's on the Vulkan material shader. So we can actually get rid of that. And I believe, so we'll actually have to come back and revisit this logic in a bit. Okay, so that means in the renderer backend, we can now just remove this because we don't need that anymore. Okay, I believe that was actually all the changes that we need to make to that for right now. So actually, one other thing that we need to do is in the renderer front end, we have this logic here that we did to load textures, to create and load textures. These things are actually not going to be here anymore. We're going to move these over to the texture system itself. So I'm actually going to snip out load texture and create texture out of here. And with it, I'm going to take this define and include for STB image, because we don't need that here either. And I'm going to move this to texture system. Okay. And I'm still going to have a to-do here, right, because we still need to split this out to a resource loader. But for now, this is going to also handle the resource loading. Okay, so let's take a second to map out what our texture system state is going to look like, right? So we're going to type def a structure called texture system state. And the first thing that we're going to do is we're going to hold on to a copy of the config that is passed in into create. Okay. And the next thing that we want is we want to hold on to a default texture, right? So that's where this is going to live for now. And next we want an array of registered textures, right? So this is just going to be a quote-unquote dynamic array, but we're actually not going to use dynamic allocation to handle this. I'll show you guys how we're going to actually set that up here in a second, but this is going to be an array of textures that we're going to hold on to. And then we're going to have a hash table for our texture lookups, right? So these two are going to work in combination with one another to be able to handle our textures, okay? Now, we also need something called a texture reference. And this is a simple structure that maintains a reference count, something we're going to call the handle, which is the ID or index of the texture, and whether or not that particular texture should auto-release. Okay? So this is where that auto-release is going to wind up being stored. All right. Next, we're going to need a static pointer to our state pointer, which holds our system state. Okay? So the very first function that we have in here is our texture system initialize. So first, it takes a look at the configuration and says, well, if the max texture count is 0, that's rubbish, can't do that. Bleat about it and return false. We failed to initialize, okay? Next, we're going to go ahead and calculate this memory requirement, right? And to do that, we actually need to figure out how much we need to store this entire state, as well as this array, as well as the extra memory block that is required by this. So to do that, our block of memory is basically going to contain the state structure first, and then a block for this array, and then a block to be used by the hash table. Okay? So we're going to keep this struct requirement, which is the size of our actual struct. That's this whole thing here. And then after that, directly after that in memory, we are going to have our array requirement, which is figured out by calculating the size of a texture times our configuration max texture count. And that's going to give us the space required for our array. Similarly, our space requirement for our hash table is the size of a texture reference, because that is what that holds, times the max number of textures. Okay? And then, simply put, we dereference our memory requirement and set that value to the struct requirement plus the array requirement plus the hash table requirement. And that will give us enough memory to hold all the information that we need to hold. And we allocate it all in one shot, and we can just use different portions of that block of memory for the different bits that we need. Okay? So at this point, if we do not have state passed here, then all we've done is calculated the memory requirement, and we should return true, because it's not necessarily a failure. We just need to know by whatever's calling this how much memory we actually need, so that's valid. Otherwise, we go ahead and we set the state pointer to state, right? Because that means we have memory here, so we go ahead and set that. And then we take a copy of the config that is passed there, and we just go ahead and set that as well. Here is where we set the array block. So we do that by taking the address of the state, right, or the pointer of the state, and adding the struct requirement. So we basically move to the end of the struct, and that is where our array block sits. And we set the state pointer registered textures array to that, right? So it basically just sort of performs a cold cast and uses that block of memory within that whole big block of memory to hold our texture array. And then we basically do the same thing for our hash table block, right? So that's immediately after the array. So we just take the array block address that we have here and add our array requirement, or space requirement for that, which moves us to the end of that array. And then we say, okay, well, that's where our hash table block starts. And we take that and we pass it on to hash table create, right? So we use that here. So hash table create, we say the element size is the size of a texture reference. The max number is our max texture count. Here's our block of memory. This false is indicating that we are not using pointer types, right? And then we store that in the state pointer registered texture table, right? So we just pass the address of that. Okay, so the next thing that we need to do is we need to use that fill method that I discussed earlier. So what we're going to do is we're going to fill the hash table with invalid texture references. And by invalid texture references, I mean we're going to default auto release to false. We are going to set the handle to invalid ID. Now this is the part that actually requires us to actually use fill, right? We could technically just rely on the zero memory operation that happens and we wouldn't need to do this. But because we need everything to have those invalid IDs, we need to go ahead and set this up. So technically this is equal to 0 and this is equal to 0, so really the only one we need to do is this. But just to make it a little bit more explicit, I'm doing it this way, okay? So we call our hash table fill and pass that through. Next, we're going to invalidate all textures in our texture array. So basically we just go ahead and grab the max texture count, we loop through each one of those individual elements, we set the texture ID to invalid ID, and then we set the generation to invalid ID for each one of those, okay? And next, we need to go ahead and create our default textures, right? And we haven't actually created this yet. We'll get to that in a second. And that is what sets up our default textures that we're going to use for various things throughout the system. So we do that, and then we return true, right? So that is all there is to this texture system initialize. Now, create default textures. What we're going to do for that is up here at the top, we're going to forward declare it. And then we're going to come to the bottom and fill it out. And all this is going to do is take this logic right here that's in our front end. Right, we're going to snag this out of here. And we're going to come to our texture system and paste that right in here. Now granted, this is only for the default texture, so this is fine for right now, but this is what that should look like. So it should basically do the exact same thing, it's just now this is kind of where it belongs, okay? So we generate our default ID, and then we go ahead and create it using the renderer, okay? And we pass that default texture name here instead of just a string default, okay? So just double check this, make sure that it matches what I have here. Now, eventually we will have other textures being created here. For now, it's just this one. So that's why this is plural, because eventually there will be others. While we're at it, we're also going to have a destroy default textures, which takes in a pointer to the state, and then basically just calls this destroy against each one of our default textures. Right now, we only have one. Okay, so with that, we also need to come up here to the top, and we need to forward declare that as well. Okay, and then finally we are going to forward declare one more method called load texture. And this load texture is basically what we snipped out of the front end. And so we're just going to basically re-add that here all the way to the bottom. So after default, destroy default textures, we'll paste this in here. Okay, and so it's still making some assumptions here about where these textures are loaded from. Again, a lot of this file loading stuff will wind up eventually being moved off to a resource loader. So for now, that's still handled here. It is what it is, okay? So everything in here should be mostly the same. So we should be good to go as far as that's considered, okay? All right, so that is actually most of the work here. Now all we have to do is fill out the actual new logic that we have. So we've done initialize, right? So this is initialize here. Let's go ahead and do shutdown, and actually shutdown is pretty straightforward, so I'm just going to paste that in here as one block. So if we have our state pointer, we're basically going to destroy all loaded textures. So this is any texture that still has a generation that is not equal to invalid ID, meaning it's been loaded. We're going to go ahead and call the renderer to destroy that texture so we don't get errors when we shut down. And then we'll call destroy default textures, okay? And then obviously set the state pointer to 0. So next we have our acquire and release methods. So we're going to define the acquire first. Again, this takes a name and whether or not auto release should happen, and then returns a texture pointer. So the first thing that we want to do is check to see if we are requesting the default texture name, and this is where that string equal I comes in, the case insensitive string comparison, right? So we take the name and say, hey, is it equal to default in any way, shape, or form? If it is, then we should not be trying to acquire it this way, right? We actually have a different method that we want to use for that, right? Called our get default texture, right? So we should be using that instead. So this is going to warn us about that, but then return it anyways, right? Because we don't want to break the application. We just want to make sure that the user is aware that they shouldn't be doing that. Okay. Next comes our texture lookup. So the first thing we're going to do is create a texture reference just to hold on to locally. And then we are going to look at our hash table and say get the entry for the name that we passed in, right? So we pass the address of the table, the name, and then we're going to write out to this reference, right? So we're going to only do this obviously if we have a state pointer. If we don't have a state pointer, then we're up the creek without a paddle. And in fact, if we do that, we are going to bleat about it, and we're going to say texture system acquire failed to obtain texture, null pointer will be returned. And that's if the state pointer doesn't exist, or this fails for some reason, we'll go ahead and return a null pointer. This should basically never happen unless the user is passing really stupid stuff. Okay. All right. So the first thing that we want to do is once we have our texture reference, we want to check to see if the reference count is 0, meaning this is the first time it's been requested. Only the first time a texture is requested can the auto release actually be set. And we're doing that so that you can't change it back and forth every time you request it, right? When it's first requested, you can either set it to auto release or not, and that's it. Until it's completely released out of the system and re-requested, you can't actually change it, right? So we go by the reference count to say if that's 0, then we go ahead and set this. Otherwise, we do not, and we completely ignore this, okay? So once we've done that, we go ahead and increment the references reference count, okay? And then we go ahead and we check the handle on that. And if the handle is invalid ID, then that means that there is no texture here. And we need to find a free index, right? So the first thing that we do is we take a count of the total textures, right, the size of the array, create a pointer to hold our texture, and then we're going to loop through all of our registered textures, right? And we're going to check here to see if the texture ID at that particular index is invalid ID. If this is true, then that means that there is no texture at this slot and it's a free slot. Okay, so that means a free slot has been found, and then we want to use the index as the handle, right? So we set the ref.handle equal to I, the index, and then we set the t equal to the address of the state pointer registered textures at that index, okay? And then we break out of the loop, right? So at this point, we found a free slot, okay? Now, obviously, there is the edge case that this thing could be full, so we need to make sure an empty slot was actually found. In other words, if t is null, right, which we should probably actually set that to null, okay? So if it's null, or the ref handle equals invalid ID, meaning the ref handle was never set by this, meaning nothing was found, then we have a fatal error. And we say, hey, we tried to acquire this, but we can't hold any more textures. Adjust the configuration to allow more, and we return a null pointer. Okay. Otherwise, we go ahead and create a new texture. So we do that by calling our load texture method. We pass the name, and then we pass t, which is our pointer to the texture, right? If this fails for some reason, then we bleat about it and return a null pointer. All right. So next, we also need to use the handle as the texture ID. So in the texture, we set the ID to the ref handle, right? So all these things interconnect. So once that's done, we're actually going to output a trace message for now, just to sort of let us know what's going on with that. So we're basically just going to say texture does not exist yet. We created it, and now the ref count is whatever the reference count actually is, which typically should be 1 in this case. If for some reason, such as we have a loaded texture already at this, right, and the handle is not invalid ID, then all we actually need to do is just, since we already increased the reference count here, we don't actually have to do anything else, right? Everything is actually going to be set up for us as needed, right? And so what we'll do here is we will say texture name already exists, ref count increased to, and then spit out the reference count, okay? Once that is done, we need to update the hash table with the reference, right? Because if we were to just return at this point, this reference is just a local copy of that. We haven't actually fed that back to the table, right? So we call hash table set against the name and pass back in the reference. And then we go ahead and return the address of the state pointer registered texture at the ref handle. Okay, so we return the address of that, and now we have our texture acquired, right? So this is how we are going to manage our reference counter for textures, okay? Now, with all that in mind, releasing works very much the same way. So what I'm going to do is, instead of going through it piecemeal, I'm going to paste the whole thing and explain it. So first, if we try to pass the default texture name as name, we cannot release the default texture. We don't want to allow that from the texture system. So if that happens, we're just going to ignore it, okay? Next, we go ahead and we get a reference. If the reference count is 0, meaning it's already zeroed, then we're going to warn that we tried to release a non-existent texture, right? Because if it's 0 before we've even tried to release it, then that means there's nothing there, okay? However, if this does not happen, then we go ahead and decrement the reference count. And now we check to see if it's 0, because if it's 0 and auto release is set to true, then we need to actually go ahead and release it. So to do that, we obtain a pointer to the registered texture. We call render destroy texture on that. We go ahead and we zero out the memory of that texture, okay? And then we go ahead and set the ID and generation back to invalid ID so that it's fresh and ready for a new texture to be loaded in this place. We reset the reference, so the handle and auto release, we reset those things to invalid ID and false respectively. We also output a trace message to say we released this texture unloaded because reference count equals 0 and auto release equals true. Or if the reference count was something other than 0 or auto release was not set to true, then we say we release texture now has a reference count of whatever it is, and then auto release is either true or false. Okay. Once we've done all that, we go ahead and update the hash table again, and that is it. We don't actually have to return anything, right? Obviously, we also need to handle the else case of this. So if we don't have the state pointer, or for some reason we can't find the reference here, we spit out an error saying texture system release failed to release texture, blah, 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 and leave it at that, okay? If we ever had to debug that, we could just set a breakpoint there and go from there. Okay. So last but not least, right below that is our final method, which is texture system get default texture, right? And all this does is check to see if we have a state pointer. If we do, return the default texture's address. Otherwise, we're going to throw an error saying we've called, let me update that. That should be texture system get default texture before texture system initialization, null pointer returned, and then return a null pointer. I actually think somewhere up here, when we were acquiring, we also said get default texture. That should be texture system get default texture. Okay, and I believe that is actually it for our texture system. So it's kind of a lot of work to get here, but you know, it's going to be a lot more flexible. Okay. All right, so I know we're covering a lot of ground in this video, but I'm going to keep this going because we're almost there. All right. So the next thing that we need to do is actually initialize our texture system. So to do that, we need to go to core application.c, and at the top, right below our renderer front end, we're going to create a new section for our system includes and include our system's texture system. And as you might expect, we need to add something to hold our memory requirement and our state for the texture system. So we're adding that there to our application state. In our initialize, right after the renderer subsystem, because this relies on the renderer subsystem, we will initialize our texture system. And this looks a lot like a lot of the other systems, right? So we set up our config, we set our config's max texture count to 65,536. That should be more than enough textures. We can fine tune that if we need to, but that should definitely give us enough space to work with for the foreseeable future. I can't imagine having that many textures all loaded at once ever. So next we have texture system initialize. So here is where we call to get the memory requirement. So we pass 0 to the block of memory to get that memory requirement. Then we allocate the memory from our linear allocator. Then we go ahead and call this again, checking the result this time to make sure that the initialization happened. If that failed, we bleat about it and return false. Okay. So since we have that, we also need to shut down. So down here in the end of our run after our loop exits, this time before the renderer system shutdown, we go ahead and shut down the texture system, right? And that is actually all we need to do at the application level to start that up, okay? All right, back to our renderer front end. There are a few more things we have to fix in here. So first and foremost, in our debug on event, we need to change a couple things here. So before we actually increment or change our choice, we need to save off the old name so that we can release it, right? So we take whatever the current texture name is and we save that off here to old name, okay? Then we go ahead and we increment our choice. And instead of loading up the new texture, we're going to acquire it, right? And instead of calling the now non-existent load texture, we are going to call test diffuse and then set that equal to texture system acquire, passing the name, and we want to auto release. We can turn this on or off, doesn't really matter. For now, we'll turn it on. Okay. And then we need to release the old texture, right? So the old texture is basically just going to be released by the old name, which is why we save this off. Now this is giving us an error because I believe the test diffuse here is not a pointer. So we need to actually convert that to a pointer because the texture isn't actually stored or owned here. We only have a pointer to it now. Okay, so that fixes that. Also, we have this default texture in here. This is actually also something we should no longer be doing, so let's remove that because that is now stored in the texture system itself. This also means our backend default diffuse and default texture, this doesn't exist anymore, so we can actually remove that. All right, our create texture here, this doesn't exist anymore, so we can remove this, right? Because we don't need that anymore. The renderer system shutdown, this doesn't own or manage these textures anymore, so we can remove both of these destroy textures because those are handled by the texture system instead. So we don't need that. And then down here in draw frame, we actually need to make some modifications to the way that this works. So right now we are using passing through this test diffuse, but that may or may not exist by the time we call this. So we actually need to put something in here to say if it does not exist, we need to use the default texture. So the way that we're going to do that is check to see if this is a null pointer. So if that does not exist, then we go ahead and set that equal to texture system get default texture, and then we go ahead and pass that through, right? So that fixes that potential issue. And I believe that is actually it as far as the renderer front end changes are concerned. So let me just go ahead and make sure everything's saved. It is. So the last bit of logic that we need to change is actually in the material shader itself. So most of this logic can actually remain the same. The only thing that needs to happen is instead of this having a direct pointer to the texture, default texture, we need to point that to texture system get default texture. And we can see that we actually don't have that defined, so we actually need to include our texture system up here. Okay, and I believe that I think is actually the only change that we need in here. So let's go ahead and build this. It looks like we missed a couple things. We'll wait till this finishes, see what those warnings are about. Okay, so our test diffuse. Oh, okay, so we are missing our texture. So this right here is just telling us that we don't actually have our texture system acquire included here, right? So we actually need to include systems texture system here. So let's go ahead and rebuild that. Looks like we still have a warning for something. Oh, I think I see what it is. Yeah, so this was passing the address of test diffuse, but test diffuse is now a pointer, so we don't want to do that. So let's go ahead and build that one more time. Okay, no warnings. Let's go ahead and run. All right. And looks like we are getting some errors in here. So it's kind of working, but kind of not, right? And so there's actually a couple things that we've missed. So the reason that this isn't updating all the time is because in our shader, when we go to update the object, update the sampler, right? We actually are checking the descriptor generation against the texture generation, right? But if we swap out the actual texture, and those texture generations are the same, meaning they've both been loaded once, for example, this check is actually going to pass, and it's not going to give us what we actually want, right? And so we actually need to add a texture ID and a check for the texture ID, right? So in order to do that, what we're going to do is we're going to add something else to the descriptor state. So if we go here to our Vulkan descriptor state, this is in our Vulkan types INL. We need to add one more thing. And this is going to be our IDs, and this is going to be texture ID, right? And so we'll check both the texture generation and the texture ID to see if either one of these has changed. And if one of those has changed, then we know we need to update the descriptor, okay? This also means that back in the Vulkan material shader, we need to add some things, okay? So our Vulkan material shader acquire resources. We set the generation to invalid ID, but we also need to set the IDs to invalid ID, okay? We are also going to need to do that when we release, right? So we're going to need to set that there as well. And then when we go ahead and update the object, right below where we get the descriptor generation, we are also now going to get the descriptor ID, or just a pointer to that, right? And so right before this check for the generation, we are going to insert another check to check the descriptor ID against the texture's ID to make sure that they match. And if they don't, that's going to be another piece of criteria that tells us we need to update, okay? And so obviously when we sync the frame generation, we're also going to have to sync the descriptor ID to the texture ID there as well, okay? So let's go ahead and build one more time and run, okay? And it looks like we're still okay. Let's go ahead and press T a couple of times to reload. So our swapping texture looks to be failing. Texture system cannot hold any more textures. Adjust configuration to allow more. So that's very strange. Why are we getting that error? Let's take a look at our texture system. Oh, I see what happened. So I'm pretty sure this break is supposed to be there. I don't know how it wound up here, but yeah, it should be in this. So if we hit this, then we should break. I think that's the issue. Let's go ahead and build, run, scroll past all this, right? So that's our current console. And now we can swap. And if we take a look at our console, the first time we go ahead and do this, we say texture cobblestone does not exist yet, which it doesn't. Created, ref is now 1. And then it says try to release non-existent texture paving 2. That is because we started off in the front end. That is because we started off here at the end with our static choice 2, right? So it's saying just release this. It hasn't been loaded yet, so it throws this warning. That's fine. That's just an artifact of our sort of debug behavior here, so I'm fine with that. Next, it goes ahead and says texture paving 2 does not yet exist, created, and then it released texture paving. Texture unloaded because reference count equals 0 and auto release is true. So we know our auto release works, right? Let's go ahead and flip this to false and make sure that that works as well. So I'll go ahead and run this. Hit T a couple times, scroll all the way down here, and we can see that we got the same message here, that the texture didn't exist yet. We've created it. We tried to release paving 2, doesn't exist yet, that's normal. The next time we say paving doesn't exist, created, and then we release the cobblestone, which is the first one we created, now has a reference count of 0, but auto release is false, so the texture was not destroyed as it was before. So we know that both of those options are indeed working. So let's go ahead and flip that back to true and rebuild one more time. And I'll run. And so now we have our texture system up and running, right? And this just provides us with a lot better of a way to handle textures in the system versus shoving all of this logic into the renderer, right? Now, obviously, we still have some debug stuff in there, but we've been able to get rid of a lot of that and offshoot a lot of the texture loading and handling onto its own system so that things are nice and decoupled, okay? Anyway, that's going to do it for this video. I know this one's pretty long. This is probably going to be the longest video, one of the longest videos in the series, I would imagine, but we had a lot of ground to cover, so I wanted to make sure that all of this was sort of done in one shot. So next we're going to start looking at materials, and we are going to start building out our material system on top of this texture system and utilizing some of the things that we've already built so far. So anyway, thank you guys so much for watching. Please hit the thumbs up button if you liked the video. Consider subscribing if you haven't already. Hit the little bell icon there to get notifications as to when videos in this or other series drops. And don't forget to drop by the Discord server. Anyways, I'll see you guys next time.